So motion sensors are transforming the way we track physical activity and monitor health, but they're not a perfect solution. They're prone to errors. One of the most common problems in motion tracking is motion artifacts, which occur when external factors introduce noise into sensor readings. Imagine you're riding in a car while wearing a smartwatch. The accelerometer inside the watch detects movement, but is that the motion due to your own body moving or simply the car accelerating? Similarly, if you are running on a treadmill but holding onto the rails, your smartwatch might detect fewer steps than you actually take because your wrist isn't moving as much as it normally would. These types of errors are particularly problematic for activity recognition algorithms, which rely on pattern analysis to classify movements. If the data is contaminated with noise from unintended motion, the algorithm might misclassify activities or overestimate energy expenditure, for example. To address this, manufacturers again use sensor fusion techniques, combining accelerometer data and gyroscopes, heart rate sensors, and machine learning models to filter out incorrect readings. More advanced wearables also apply context-aware algorithms, which consider external factors like GPS, altitude changes, and previous movement history to improve accuracy. Another issue is sensor drift, and this is something that mainly affects gyroscopes. You see, unlike accelerometers, which have a fixed reference, gravity, gyroscopes accumulate small errors over time, and this causes them to lose accuracy. A gyroscope might initially track your movements correctly, but after a few minutes, it may start reporting slight rotations even when you're perfectly still. This is a big challenge in applications requiring precise motion tracking, like during sports performance. Over time, even a tiny drift can lead to large discrepancies in orientation estimates. To correct for this, many IMUs also include magnetometers, which detect the Earth's magnetic field and provide a stable reference point. But magnetometers introduce their own problems. They can be thrown off by metal objects and electromagnetic interference, making them unreliable in certain environments. Another common issue is calibration drift, where sensors lose their accuracy due to temperature changes, aging, or mechanical stress. If a smartwatch isn't properly calibrated, it may underestimate or overestimate step counts, misclassify activities, or even fail to detect falls. To compensate for these issues, a lot of devices include self-calibrating algorithms which periodically recalibrate sensor baselines based on known motion patterns. Another issue stems from the fact that motion tracking is computationally expensive, and frequent sensor sampling drains battery life. High-end smartwatches like the Apple Watch and Garmin devices use continuous motion tracking, but this comes at the cost of shorter battery life. To extend battery performance, some wearables use low power modes, reducing the sampling rate of motion sensors when the movement is minimal. For example, if a smartwatch detects that you are sitting still, it may switch to a low power motion mode, sampling accelerometer data less frequently. When movement resumes, the device reactivates full tracking, but this trade-off can sometimes lead to missed motion events, especially for activities that involve subtle movements like stretching or yoga. More recently, some wearables have started to use adaptive sampling rather than just low power modes. For example, Apple Watches and Garmin devices adjust sampling frequency dynamically, only recording at high precision when motion is detected. And then you have the issue that not all wearables use the same motion tracking algorithms. A step counted on a Fitbit might not match the step count from an Apple Watch, and a workout session recorded on a Garmin may have a different calorie estimate than the same workout on a Samsung Galaxy Watch. This variability is caused by underlying differences in sensor placement, algorithm design, and data processing techniques. Essentially, each company uses its own proprietary signal processing methods, and this makes it difficult to compare data across devices. While there are some standardization efforts underway, there really is no universal benchmark for motion sensor accuracy in consumer wearables, or any other sensing modality for that matter. This makes it really difficult for researchers to leverage wearable data at a population scale to better understand public health, or even to validate wearable data against gold standard motion tracking techniques.